Welcome students. In the last lesson we learned about ionic bonding, and we learned that it was one particular type of bonding where you have a metal bonded to a non-metal. Now the bonding doesn't begin and end there. There is another type of bonding which is referred to as covalent bonding. And we will explore these couple of questions in class tomorrow. So the first slide here we will handle tomorrow in class. However, let's move on. So we mentioned that the first type of bonding was ionic bonding. The second type of bonding is covalent bonding. Now covalent bonding is a different type of bonding. It's a different category of bonding, and that happens between a non-metal and non-metal. It's also formed when the electronegativity difference is less than 1.7. We'll talk soon about what electronegativity difference is. It's a property that you'll find on the periodic table. Covalent bonds can also be broken down into two different categories, polar and non-polar. Electrons are shared between atoms. If you remember with ionic bonding, the electrons were transferred. So now the electrons are not transferred, rather they're shared. So they have the electron for a certain amount of the day or week, or whatever you want to look at it, whatever way you want to look at it. Covalent bonds are as strong as atoms become part of each other. So within a covalent bonds, the atoms are actually because the electrons are shared, the atoms become part of each other. And this is another important one: covalent bonds do not conduct electricity. So opposite to ionic bonds in that regard. Okay, so how do I know whether ionic or covalent bonding will form between atoms? Well, you've got two criteria. Number one, have a look at the atoms that form. If it's a metal and non-metal, it's going to be ionic. If it's a non-metal, it's going to be covalent. So let's look at two examples of that. So first example is a very common one. We could say sodium chloride or potassium chloride. Those are ionic because you have a metal. Sodium is a metal, or potassium is the metal in that regard. But if you look at something like HCl or in the H2O rather, you have hydrochloric acid and water. So you can see in both of those instances, HCl and H2O, there are no metals. So just non-metals, and therefore they would have covalent bonding. The second way that you can tell whether something is covalent or non-covalent is to have a look at the electronegativities for each of the individual atoms. Now, how do you find that? Well, it's shown on a lot of periodic tables. So if you look at your periodic tables, generally you will find that you can see electronegativity value. So there's a periodic table showing electronegativity values right here. And we're going to try and find out whether we can find out from that whether it was ionic bonding or covalent bonding. So for potassium chloride, if we look at the electronegativity of potassium, so we have a metal, which is potassium, that has an electronegativity value, and you can see it right here. It's 0.8. Chloride comes from chlorine. That is the non-metal. It is the ion for chlorine. And its electronegativity value you'll find way over here on the right of the table. And the electronegativity value is 3.0. 3.0. So if you take the small value away from the big value, there you're going to get an electronegativity difference of 2.2. And so sometimes you show difference values with the triangle. Electronegativity, sometimes we write as En. So the electronegativity difference is 3.0 minus 0.8, which is equal to 2.2. Now the guideline, remember, was if it's greater than 1.7, it's going to be ionic. And so that tells us the second way we know that potassium chloride is ionic. Not only it has a metal in it, but also within the structure has a metal, and the electronegativity difference is quite big between the two of them. Now, the electronegativity difference is a measure for how much the atom wants to receive another electron. So you can see that chlorine had quite a big electronegativity difference. What that means? It has one of the highest electronegativities. It means that chlorine really wants to take on another atom, to get another electron rather, to get a full outer shell. Fluorine has the highest electronegativity difference, and that is a value of 4. And that means that out of all of the elements in the periodic table, fluorine is the most electron hungry. Okay, if you go over to the left-hand side of the table and look at the metals, conversely, they have very low electronegativity. So what it's saying is that an ionic bond forms between atoms with low electronegativity and atoms with high electronegativity. One atom wants to give away the electron, the metal, and one wants to receive it, the non-metal. So another example of that would be calcium bromide. Calcium bromide, again, is, if you look at calcium bromide, the first thing we ask is there any metals? Yes, there is. And if we look at the En difference for calcium bromide, calcium is a metal, but even disregarding that, calcium has an electronegativity of 1. And bromide comes from bromine, and that has an electronegativity of 2.8. Okay, so 2.8 minus 1 is a difference of 1.8. Chances are very high that will be an ionic bond. Okay, so if we look at an example of a non-ionic bond, a covalent bond, let's take H2O. H2O, we look at the electronegativity difference. Now we also know that there is no metals involved, so it should be covalently bonded. But the electronegativity difference, we're going to look at our chart, and we find that hydrogen has 2.1 and oxygen is 3.5. Okay, so 3.5, 2.1. Now some students get confused because there's 2 hydrogens, but you don't have to use or in any way use the fact that there's 2 hydrogens. You just take the raw electronegativity value. So it's 3.5 minus 2.1 is 1.4. Less than the required 1.7. Therefore, it will most likely have ionic bonds, covalent bonds. Most likely have covalent bonds, non-ionic, okay, because the electronegativity is much smaller. Okay, so that's 2 different ways that we would know. So there's 2 categories of covalent bonding, and again we look at the electronegativity for that. So when electrons are shared equally, so think about the electron being shared, you know, for 12 hours of the day by one atom, 12 hours a day by another atom. It is called non-polar covalent. There is no polar opposites. So when we think of polar, we might think of the North Pole, we think of polar opposites. And there is not much in the way of electron hungriness. There's not much difference between nitrogen and chlorine. So these are referred to as non-polar covalent. If we look here, so non-polar covalent, and we look at nitrogen. So nitrogen is got an electronegativity of 3, and chlorine also has an electronegativity of 3. So if we take the electronegativity difference, it is 3.0 minus 3.0, which is 0. So there is no electronegativity difference. What that means is that the nitrogen and the chlorine both want an extra electron around the same amount. So it is shared because it's a covalent bond. It is not transferred. They are both nonmetals. And so the question is, how is it shared? Is it shared equally or is it shared unequally? And in order to figure that out, we have to look at the electronegativities. If the value is less than 0.5, generally we can say that it is non-polar. And that means, what non-polar means is it's shared equally. Okay, so it means that when you have a nitrogen and a chlorine, by the way, when we set this up, and you'll see, as we've already talked about, look at the number of lone pair electrons in the nitrogen, and you will see that it has 3. Okay, it has 1, 2, 3. Now that means that nitrogen will form 3 bonds in the covalent structure. It will form with a chlorine here, and it will form 3 of them, and chlorine will just need 1. Remember, chlorine just needs 1 to complete its outer shell, and so nitrogen will need 3. Nitrogen has 5, it needs 3 more. And so what happens is, this electron, chlorine electron, and this electron, they're actually shared. And the second one is shared, and there's another one shared over here, if you like. And so the nitrogen bonds to 3 chlorines. So the formula for that would be NCl3. In terms of Lewis dot diagrams, the first question you should always ask is it ionic or covalent bonding? If it's ionic bonding, we use the square brackets. If it's covalent bonding, it means the electrons are shared, not transferred, and we don't need to use brackets. And we use the lines just to show that the 2 electrons are shared. So chlorine is happy. This chlorine is happy. It now has a full outer shell because it's sharing 1 from the nitrogen, 1 here from the nitrogen. This chlorine is happy because it's sharing that nitrogen, and this chlorine is happy. The nitrogen is also happy because it's got 1 each from the chlorine that's shared. Okay, so the two of them are both happy. They've got a full outer shell, and remember, that's how we get happiness. Okay, so the 2 different categories of covalent are nonpolar and polar. So an example would be fluorine, where we write in it's got 7 in its outer shell. This one's also got 7. We know that the electronegativity differences of fluorine is 4.0 minus 4.0, which is going to be 0. So we know it's going to be nonpolar covalent because that's less than 0.5. The other thing is, how would you write this in terms of a Lewis dot diagram? Okay, so in terms of Lewis, we're going to have the fluorine and the fluorine. They both just need to share 1. So we've got that 1 electron that's shared, and then we've got the rest are filled in. Okay, so you fill in the 7, and 1 of those 7s on either side is going to be shared. Okay, so you have, and that's shown with a line. So the F are bonded together, and it's a shared paired bond. Okay, it's a non-polar covalent, and what that means is the electron, if you were to look at the electron is shared evenly between the fluorines. Right, so it's shared nice and even. However, that's a non-polar. For a polar covalent, if we look at the En difference between the 2 of these, and we go back and look at our En table, we'll see that hydrogen has a En of 2.1, and chlorine on the table has an En of 3.0. So it's 2.1 and 3.0. So 2.1, 3.0. So the En is going to be 3.0 minus 2.1, which is equal to 0.9. And that is actually greater than 0.5. Greater than 0.5. Therefore, it is polar. And what that means is that there is almost an ionic characteristic to the bond, and it means that they are not shared evenly. So if we look at the 2 types of bonding, and we look at the hydrogen is here, chlorine is here, and we put in 7 electrons for chlorine, we put in 1 electron for hydrogen, and we now say that these electrons in here are shared. and the electrons are not shared evenly because the chlorine is more electron hungry. So it would look something like this. Maybe it takes a little bit more, and then it comes over here, and the electron takes a little bit more. And so basically the chlorine is going to want the electron more. And what that does is it creates a small charge. It's not like an ion, but it's similar. And we think of polar opposites. And so charges are also opposite in that regard. Plus and minus are the opposite of each other. And so what happens is the chlorine develops, because it has the electron more, it develops a slightly negative charge. Okay. And the hydrogen develops a slightly positive charge because it does not have the electron as much as it needs it. Okay, so that's the difference between polar and non-polar. In polar, you will have a slight charge, and the electronegativity values are also representative of that. They're very different. Okay, and so just some tips when you're drawing a Lewis structure. Confirm whether it's ionic or covalent. Draw the Lewis for the elements. Note the number of unpaired valence electrons, and then add elements in until the correct bonding ratio is achieved, and draw lines between the shared electrons. Okay, so you could try practicing do one for nitrogen and hydrogen as an example. Now, naming covalent molecules is quite simple. And the first element is named first. The second element is named using the suffix "ide." That is also the anion. Always second is the anion, which is the negative one. And prefixes are used to denote the number of atoms. Mono is not used to name the first element, but it will be for the second element. And the numbers on the left represent how many of the atom you have. So if you've got 2 atoms, you use the prefix di. If you've got 3, you use tri. Let's use an example. Okay, so one we're very familiar with. We do not put in, if there's only 1 at the beginning, we don't need to put in mono in the first atom. But you'll see that there's actually 2. And so up here, di represents 2. So it's dioxide. Using the same logic, we do not need to put in that it's mono on the first atom. But on the second one we do, and there's only 1 oxygen. Okay, we'll do one more. The first one is silicon. There's only 1 silicon. So it would be mono, but for the first atom you do not have to put in mono. You would if it was di or tri. And there are 4 fluorines. So we're going to have to use tetra. Tetrafluoride. Okay, the final one I'm going to do is there is 2 phosphorus, so it's di. You do have to put in if it's non-mono. Diphosphorus. And then how many sulfides is there? How many sulfurs is there? Well, there's 3, so you use tri. Okay, so we've covered covalent bonding. How do we know that covalent bonding has happened and it's not ionic bonding that's occurring? How do we draw the Lewis dot diagram for a covalent bond? And also, how do we name covalent bonds? So we will review later, tomorrow in class, we'll review ionic and covalent bonds, and the next lesson will be posted shortly.